Hello everybody, thank you for joining me again. Root Beer here. We're going to be dealing with the 2003 Friar. Now we've done 1, we've done 2, we've done 3, we've done all the other questions. Now in this video, we're going to be doing question number 4. Okay? So we've come a long way. It's the very first question. Once again, I'm ignoring the extensions to problems. I'll do them if there's enough demand. But really I'm trying to focus on the core contest. So question number 4, let's take a look. Alright, question number 4, here we have it. For the set of numbers 1, 10, 100, we can obtain 7 distinct numbers as totals of one or more elements of the set. These totals are 1, so 1 by itself, 10, 100, 1 plus 10, 1 plus 100, 10 plus 100, and 1 plus 10 plus 100. Okay, so all the possible different combinations that we can get. The power sum of this set is the sum of these totals, in this case 444. So 1 plus 10 plus 100 plus 11 plus 101 plus 110 plus 111, that should equal 444. Okay, A part. Question A. How many distinct numbers may be obtained as a sum of one or more different numbers from the set 1, 10, 100, 1000. So we just added one number here. Calculate the power sum for this set. Okay. So, in terms of distinct numbers, it's probably best. There's only 4 numbers we can be using, so I think at most there's 2 to the 4 numbers we can be getting. So it's best maybe to just try and write these out, see what numbers we get, see if there's a pattern, and then calculate the power sum for this set, and maybe there's a pattern there as well. That might help us for the rest of the question. We'll see. So, our set is 1, 10, 100, and 1000. So they're all powers of 10. That might be important. That sort of jumps out on the page at us. Let's just calculate possible sums. So it's best when you're doing something like this to do it methodically. You know, pick a method of calculating things out. Don't just say, oh, 1 and 100, 10 and 1000, 10 and 101. You gotta have a way of doing things. So I'm going to sort of have 1s all in this column, 10s all in this column, hundreds and thousands, and we're just going to sort of add them one at a time. So 1 by himself is equal to 1. Let's do all the ones that don't require 2 things first. So 10 by himself, 100 by himself, and 1000. So there's 4 different sums, although I guess I don't really consider those sums what the problem does. So now combinations. How about 1 plus 10? Well, we already know that one's fine. How about 1 plus 100? 101. 1 plus 1000. 1001. And so that does it for sets additions of 2 numbers that involve 1. So let's add 10 and 100. 110, we've seen that before. That was given to us at the start of the problem. And there's one more. Okay, so that does it for 1, 2, 3, 4, 5, 6 of them. There should be 4 that use 3 of these numbers. That's 111. You know what comes to mind, if you're familiar with it, I know it's the sort of 9th grade contest, but if you are familiar with it, these numbers look an awful lot like binary. So that's base 2 numbers. Obviously, we're working with tens and hundreds and things like that, but you could probably consider this sort of a binary thing. And then that would help you count how many that you could have. But we've done all the ones with 3. We just have one more to do. That's the last one, the one that involves 4. All 4 numbers added together, 1, 1, 1, 1. Okay? So we were asked how many distinct ones can we get. Remember the sort of empty sum, the sum of nothing does not count. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We were asked for the number of distinct sums. Well, we can check all along the way. These are all distinct. If we do 1 plus 10 plus 100 plus 1,000 plus 11 plus 101 plus 1,001 plus 110 plus 1,010 plus 1,100 plus 111 plus 1,011 plus 1,101 plus 1,110 plus 1,111. I'm just going to opt to use my calculator on that one, and that's okay. Calculators are allowed. For something long like this, if you want to make sure you don't press the wrong button somewhere, what you can do is break it up into smaller sums. Maybe sum the first 4 numbers or first 5 numbers, then sum the next, and so on. But if you're confident in your calculating skills, you can certainly do them all at once. So I get a sum of 8,888 is my sum. And I think it's called power sum. We're going to go back and check the question anyway because we're done part A, and we'll correct our wording if there's a problem, but I'm pretty sure it's power sum. The power sum. Okay, there's a dash there. I'm not going to bother to add the dash. Okay, so that was part A, how many distinct numbers can be obtained, and calculate the power sum. So we did that, 15 numbers, and it gave us 8888. B, determine the power sum of the set 1, 10, 100, 1,000, 10,000, 100,000, and 1 million. Okay, so that's a little more involved. We might try and look for a pattern. Okay, notice that with 3 numbers we got 444, and with 4 numbers we got 8888. Okay, so I might guess that maybe turns out that it's 4 times the biggest number, and maybe for this one it was 8 times the biggest number. I'm just spitballing here, just trying to figure things out. And what is the significance of the 4 and the 8? Well, those are powers of 2. Something that you should probably be shouting at the screen right now. Those are definitely powers of 2, 4 and 8. 4 is 2 to the 2, and 8 is 2 to the 3, which is 1 less than the number of numbers we have. And powers of 2 and binary, there's got to be some sort of connection. So we had 7 numbers here. We had 15 numbers before. Those are both 1 less than a power of 2. So let's try and work some things out. Let's just say some things. Uh, 2 to the n minus 1. Okay. Okay. So this is something I noticed. We had 7 distinct numbers, and then we had 15, and that was 2 to the number of numbers in the set we were talking about, minus 1. So the way that works is we have all these expressions, all these possible sums of numbers. And they have to be involving 1, 10, 100, and 1,000. So how many can 1 be in? Well, like 1 can either be in a sum or not in a sum. So there's 2 choices. Can we have 1 as part of the sum or not? We have 2 choices as to whether or not 10 is in the sum. Either 10 is part of the sum or it's not. Same with 100, same with 1,000. So there's 2 choices for if 1's in the sum, 2 choices for 10, 2 choices for 100, 2 choices for 1,000. So that's 2 times 2 times 2 times 2. That's 2 to the power of 4 possible sort of sum expressions. So you'd think it'd be 2 to the 4, but you cannot have the sum expression. You can't have the empty sum. You can't have nothing. You have to have at least one number. So that's why if we're given a set, we can have 2 to the n possible choices for sums. Now, are these all going to be distinct? In general, no. But these are all going to be distinct in this case. There's no way. If we were going to have if we were going to have 2 possible expressions, we'd have something like 1 plus 10 plus 1,000 plus 10,000 is the same as 1 million plus 1 or something. We'd have something like that. At which point we'd be able to equate powers of 10 added up together. Shouldn't say different, we should say single powers of 10. To get the same, actually, the same number. So I haven't explained myself the best, but I have given what I think is a good justification, an okay justification for why all these sums will be distinct. Okay, if there were a way to add single multiples of powers of 10 together, you'd be able to say that, well, this number is also the same as this number. They're 2 different expressions for the same number. Doesn't work like that. Okay? It's why the base 10 counting system is. If you have 3 10s, you can't write that as 49 or something like that. There's no way to write that any other way than 3 10s. 3 10s is 30. 30 is not also 9 1s and 4 tens or something like that. So that tells us that they'll all be distinct, and that lets us approach the power sum. Because even though we don't know what all these are, we do know they're all going to be distinct. I think we go up to 1,000,000. So we have 2 to the n minus 1 sums. Either one is in the sum, is in any one of these sums, or it's not. Pick a random expression of these terms, maybe 10 plus 1,000 plus 1,000,000. 1 isn't part of that expression. 1 plus 10 plus 100 plus 10,000, 1 is part of that. So how many expressions have a 1 in them? How many have 10? Because that'll tell us how many 1s we have, how many 10s we have, how many millions we have. So each power of 10 is either in the sum or not. So each power of 10 should appear half the time. Now I know what you're saying. 2 to the n minus 1, that's an odd number. Well, it doesn't appear in the empty sum, but we're not counting the empty sum. So we can add up 1 and still divide by 2 and we'll still be fine. Another thing we could say is what would be the best way to say it? I don't want to leave that plus 1 in there without justifying it. So he appears in half of the possible sums. Yeah, let's just clear the page and try this reasoning over again. So they appear half the time. So including the empty sum. Now we don't have 2 to the n sums that we're considering. We still have 2 to the n minus 1 of the sums. So all of them are going to appear 2 to the n minus 1 times. So we should get a formula for the power sum. So we have 2 to the n minus 1 ones. Remember, we're summing all the sums. I'll do an example in a moment to show that this works. In this case, n is 7. So for 1, 10, and oops, that should be a 100. The power sum was, it's 2 to the, so n is 3 here, 3 minus 1, 1 plus 10 plus 100. So that's 2 to the 2 times 111, 4 times 111, 4, 4, 4. And that's what we know. We were given that at the start of the question in the preamble. If we wanted to do it with the stuff we just figured out in the previous question, we'd get 2 to the 3 times 1,111, which would give us 8888. And that's what we found in part A. So 1,111,111. So that's 64 times 1111111. And if we punch that in on our calculator, 64 times 1111111, we get really big number 7111104. Okay, we just double check 1, 10, 100, so that was 3 of them, so up to 1,000,000, which is 10 to the 6, we should have 7 of them. And 2 to the power of 6, that should be 64. And indeed it is. So we just double check all that we can. We have justified our use of the formula. You know, we alluded to our previous work. We figured out how many possible sums there are. We explained why we know that they're distinct, and that's because, you know, base 10 counting system works. So we found the number of choices. We found we pointed out that they're all going to be distinct. We said that adding up all those sums is basically the same as adding up the number of ones, adding up the number of tens, adding up the number of 100, and so forth. So we just need to figure out how many of them appear. They appear about half the time. So that's 2 to the n minus 1. Got ourselves a formula. We checked to make sure it worked. That was just for us. We didn't have to really include that. But it's always a good idea to include a simple example for the markers just so they understand that you do have the right answer. So we sub in our values. Got ourselves a final answer of, what is that? 71,111,104. Okay, so a very good question indeed, and that was it. There's no C part. We're done. And once again, I'll do the extensions if you really want to. So leave a comment if you really want to see the extensions. But for the most part, I'm not planning on doing those. I'm just going to straight do Friars because this is the only year that has the extensions in them. But if you really want them, leave a comment. If you like this video, if you like this contest or the Friars, leave a comment or throw a like on the video. Or if you really want to, you can subscribe. I do lots of these math contests put out by the CMC, and maybe someday I'll do other contests. But yeah, for the most part, good contest, good first Friar paper, and yeah, we'll move on to the 2004 and also the 2003 Galois and Hypatias. But yeah, we'll leave it at that, and thank you so much for watching. Don't forget to like and subscribe, and yeah, I'll see you guys later.